לא יודע, עליי מה הילד יחד עם זה. אני פשוט לא יודע אם זה מחובר למשהו, אני צריך לשאול את מוזר.
בעיקרון הם כן מקליטים את השיעורים.
לא, אני יודע. אני הקלטתי גם כן, אבל אני לא יודע אם הוא צריך לעשות איזשהו משהו בלי בצד שלו.
הוא מקליט את השיעורים?
לא. הוא רוצה אבל להקליט עכשיו.
סתם כי לא עובד?
כי מישהי ביקשה במיוחד שיקליט. בעיקרון אבל טוב אם הוא תמיד יקליט.
כן. אני גם חושבת.
כן.
אפשר לבקש.
כן. את אלפיקית?
לא, קוגניציה.
קוגניציה? תואר ראשון?
תואר שני.
בקוגניציה?
מועצת.
וואלה? לא ידעתי שיש כזה.
כן, יש... אני שנה ג' עכשיו של קוגניציה, של תואר ראשון, ושנה מספר שנה פשוט. ואני מסיים תואר שני.
באמת? טוב.
כן.
מגניב. אז מה, תואר ראשון ושני ב4 שנים? כן?
את באיזה?
אני מדעי המוח.
איפה מדעי המוח?
זה כאילו פה?
זה לא תוכנית של זה כזה?
זה תוכנית של המכון למדעי החיים. כן, כאילו ביולוגיה.
זה 4 שנים?
זה 2 שנים.
אוקיי. ובמדעי המוח זה יש על זה?
בשיעור עכשיו.
האמת שאנחנו מעבדה ממש קוגניטיבית.
מי יכול לזה?
טוב, בסדר. בסדר.
כן, הייתי אפילו...
זה לא שיש מלא אנשים גם ככה. טוב.
מה, בכנס של הראייה?
כן.
הייתי? די. זה היה מגניב. הייתי אבל רק עד הצהריים.
אז אני הפוך.
כן.
מי שעשת שכח את זה,
יש פה עוד סטודנט שהוא תכף חוזר. הוא יושב פה, זה בטח שלו. אין בעיה, זה דוד. בסדר, אני אגיד לו. תודה.
אני שם פה
100%.
למחר בבוקר.
100%. טוב, זה שלך פה, דוד.
עשיתי לך את השיר פה. תודה. שיהיה לך נחמד שם. תודה.
טוב. רביעייה. בסדר, שבוע הבא, בהודעות, שבוע הבא אני לא אהיה, אודי יהיה. אדבר כאן קצת על דאטה מקופים. אני יכול בעצם לדבר בעברית? כן, אני יכול, נכון? אין פה מישהו שעוד הנרי וקסיה גם יהיו פה שבוע הבא. והאמת שאנחנו הולכים להתחיל לדבר על מערכת הראייה, סוף סוף מבחינתי, שזה דווקא מתאים, כי הם שניים שמכירים את זה יותר. אז קודם כל שבוע הבא נחזור קצת לבולד ולקשר שלו לספייקים, לנוירונים. ואז נחזור למערכת הראייה ונתחיל להתעסק עם אנליזות יותר מתקדמות. מי שלא יודע, שבוע הבא יש כנס של יומיים, כולכם יודעים, סבבה. הוא מדבר על דברים שלא ממש הספקנו להגיע אליהם, כי היינו צריכים להתחיל מההתחלה ולא מהאמצע. אבל היום קצת נתחיל לדבר על הדברים האלה, כי אנחנו נדבר, ואני מקווה שניגע קצת ב-PRS, Population Receptive Field. הכנס שיהיה עוד בשבוע הבא, לצערכם הוא נגמר ביום ראשון ב-2:30, וזו הסיבה שיש שיעור ב-3. אני פשוט צריך לקחת את האורחים לאיפשהו. אז אני הולך לטייל, אבל אודי יהיה פה איתכם. הוא מדבר על גישות לאנליזה, גישות תכנון בטיפול בדאטה של MRI, גישות קוראים להם coding versus decoding, זה נושא הכנס. הכוונה היא בהטמעת מודלים. Switch to English now. I'm just telling him about the next week workshop, which will deal with the decoding of MRI data, which is usually applying classifiers or correlation analysis to multivariate, taking a multivariate approach, or the encoding part, which is the approach that uses models, usually biologically plausible models like the receptor field, and try to create a certain model with certain parameters, and then try to see if the data fits into the model. So two different approaches that each can be used to ask different questions. And the idea is to go over these approaches by two really good scientists. One of them is John Winaware, who's going to be here on Sunday, and he's part of the work we're going to talk about today is his work. He's been in Brian Wandell's lab, which is a very important lab in everything to do with systematically mapping and developing tools to map the visual cortex. So, so let's start. So this should be as no being news to you. You view the image, a certain image in the world. That image is inverted on the retina, okay? And then via the optic tract gets into the thalamus, the LGN, and there the information from both eyes crosses the optic chiasm here, and is divided, and then it propagates onto the visual cortex, and there is some kind of mapping that preserves the mapping on the retina. And this is going to be the starting point for today's lecture. And what I want to cover today is the organizational principles of the various, of the different regions in the visual cortex. So some of this will be old news for some of you, some of it will be more maybe new, or some paper or certain regions that you haven't had the chance to focus on. So I hope some of it will be new. And as we go on, we will discover more and more rules or principles, and more sophisticated ways to map or to analyze the way the visual information is represented in the visual cortex. So the basic organizational principle is basically twofold. So one is the location, the preservance of the location on the retina, and thus the location in the world, onto the visual cortex, and this location reserved by systematic mapping of both the direction and the eccentricity of the stimulus, or the pixel in real world coordinates. So what I mean by that is that if you have, in this example, is the calcarine sulcus, and we talk about V1 and then V2 and so on and so forth. So calcarine sulcus, this is the medial part of the brain. We're looking from the medial part outside. This is the calcarine sulcus. And on both banks, you have V1, the bottom part, and the top part, and then V2, V3, and so on. So as you may or may not know, the neurons in this area, and indeed as we'll see in other visual regions in the human brain, and not only the human brain, the neurons here are organized in a very certain way, okay, and there's a gradient, a consistent mapping of the position in space onto the cortex. So these two neurons that are adjacent to each other, or these two voxels, doesn't matter, will respond to roughly the same position in space within the same region. So within V1 and within V2 and V3. When we cross between regions, we have change in direction and the way we map the gradients in which we map space, and we'll talk about that. And another, so this is one key organization principle. The other one is there is a systematic. So this is a. Let me highlight just what I said. So one of the things is direction. Okay. So this region, let's say this region in space, will be mapped. The neurons that respond to this region will be placed next to all these adjacent locations. And we have two axes, right? So we have the angle, the direction, if this is the fovea, the center of the eye, and we have the distance from the fovea. and the distance roughly maps along the anterior-posterior. So this is anterior, this is posterior, this axis. So the more posterior we go, we get closer to the fovea, right? And the angle, the direction parameter goes perpendicular to that. Okay, so along the far from the calcarine, and then it changes. So we'll see that in a much more clear sense in a few slides. Okay, so we have several things that we should remember or we should understand about the organization of, I'm talking now about the early visual cortex, okay? And this is true in part to later or more high-level regions. We'll get to them soon. So what you see here is a very, I'd say, classical experiment from the 80s by Tutel and colleagues. This is the one slice of the visual cortex of a cat. The cat didn't survive the experiment in the same manner he entered the experiment, unfortunately. But what you see here is, well, maybe I'll ask you what you see here. What's very clear, first of all. So this is the stimulus that was presented. Okay, these alternating black and white checkers along these circles and lines. And what you see here is staining with some variation of glucose that enters the cell, and you can stain the cell bodies. And this is actual cortex. So what you see here, it's very simple, it's not a trick question. Okay, let me help you. So what you see, here you have the, let's say, this part of the stimulus, okay, the right part of the visual screen. So this would be the left visual cortex, okay? And what you see here is the black stains are the neurons that were active, responsive to this kind of stimulus. And first of all, you can see that some level of this form is preserved, okay? Before getting into the details. So it's not that by chance we got this crisscross lines, okay? Okay, now I'll tell you that this region is the most posterior region of the cortex, so that means it represents the more foveal regions, okay? Sorry? Yes.
So why is it that the inner ring is so posterior and much more anterior?
Here or here? What are you talking about?
In the brain, I mean.
In the brain?
You would expect it to be halfway.
This one?
Yeah.
You talking about this region? Okay, let's.
Or is that just different in cats or something?
No, I'm not sure I understand the question.
In the human brain,
Right.
we have a much bigger foveal representation.
Okay, so yeah, I'm getting to that. So what you actually see here is that exactly, because okay, let's go over this step by step. And no, it's okay. What Peter said is what I'm getting at basically is that first of all we have the posterior front, posterior and anterior representation, okay, and you have this these lines that represent basically the corresponding stimulus parts. And what you have here, in addition, is exactly what I think what Peter was aiming at, is that you have some overrepresentation of the fovea, and it's not. We'll see it in a second. It's more clearly. It's not so easy to see here, but what you have here are lines, okay, that are the same width. This line and this line and that line. However, these black lines here are thinner than these and these and these. Okay. You have as you go away from the fovea, you have less and less neurons representing the same amount of space. Is that somehow? I think it's just not clear what you see here. It's not a very good image, because what you're saying, if I got you correctly, is that you thought it was the other way around. So there was no over-representation of the fovea.
Well, the image looks a bit like that.
Yeah.
Looked a bit like that.
Yeah, but it is actually what you have here actually is an over-representation. You have more staining at this part, okay, which is all the staining corresponds to a very little, very small region. Okay, so what's missing here maybe, you can see it here schematically. Okay, what's missing here is something that defines where the fovea exactly ending. Okay, when the fovea ends and the rest of the peripheral regions begin. But you can see it here in the more, what I talked about before, in a more schematic way, but more clear way. You can see the thickness of the line here and the thickness of these painted lines or painted neurons here. And what you see here is that the same, well, you have to trust me a bit, it's not that clear, but this is just the first experiment in cats, that you have an over-representation of the fovea. So this region, this one-on-one centimeter here is represented by a thicker line here than the same one-on-one centimeter here, which is represented here. Okay? Let me. I think I have something that showed that in human that explains it a bit. Not this one. This is just a schematic that explains this. But let's stick with this for a second. So what we have here is just a demonstration. Maybe it's more clear, that shows you how this part of the image, early part of the image, is represented. So of course, if it's on the left, it will go to the right cortex. It will be inverted. We know that also. And as you can see here, this middle part, if you fixate here, is represented in a larger, overwhelming large region of the visual cortex relative to the peripheral part. Okay? So this, roughly, this is just a schematic, but it corresponds to the thick lines we saw before. Okay? So that region here has these thick lines here that cover basically this whole part, and it's represented in a much larger space than the actual space it occupies in the wall. Okay? And this is because, and again, I don't think I'm telling you something new here. We have very dense photoreceptors, a very dense area of photoreceptors in fovea, and this is why when we want to attend to something, we move our eyes. We do that basically about 6 times a second without noticing, but it's a totally different story. But this cortical magnification, as it is usually referred to it, is exactly this relationship, and it can be quantified more or less by logarithmic scale. So this is, I'm trying to think if this is, yes, the first two are in cats. Oh, yeah, this one is in human. And you can see these last two are in humans. And we'll talk about functional MRI. This is, again, what we aim for, so we'll talk about it in a few minutes. But you can see more or less the same. What you see here is the eccentricity from the fovea, okay, and the cortical magnification factor. And the idea is, again, that areas, and again, think about it, you have dense population of photoreceptors, you have bundles of fibers that go from them, and they go through the LGN directly to the visual cortex, so they excite or they connect to many more neurons, okay? And again, as you go away from the fovea, you have less and less neurons representing that area, and that is why, to achieve the same acuity, you have to magnify the stimulus by 1 over the magnification factor. Okay? You want to compensate for the magnification factor. So, if I look here, I can recognize this T, but if I want to recognize this T here while I'm still looking here, I have to make the T this big. Well, not from where you're sitting now, but you get the idea. So, we have first concept, first principle, which is the magnification factor. I'm already mentioned the exact mapping, and let me do that now more systematically and more thoroughly, because this is the basis for the retinotopic mapping, and then also the receptor field and population receptor field, which we're going to talk about later. You can map the retinal domain, or the retina, which corresponds basically one-to-one to the visual world, except things are inverted, but let's forget about that. If this is the fovea, every place in space or every place on the retina, okay, can be described as the distance from the fovea and the angle of that distance. Okay, so you have two parameters, and this mapping translates in a very, very systematic way into the cortex. But there, we're not talking about this angular representation, but we're talking about this columns and rows organization, and we translate it, basically, we translate each one of the factors into a column and a row. Okay, so for example, this red square, which is at angle, let's say 0 or 180 or 90, whatever you choose, and a distance 5 will be at a distance, actually it's not the same, because I don't know who made that picture, I don't remember where it's from, but it will correspond to a certain angle, which is, I would say, 90, and a certain eccentricity level, okay, or distance from center. Now, the reason this is a circular array and this is a rectangular array is this feature corresponds to what I said before about the organization along the, let's say, calcarine sulcus or later different extrastriate regions. So, if we have this eccentricity map, right, so this is closer to the center and this is further from the center, so this will correspond to what region of the brain, or what direction of the brain. If this is closer to the center, this is further from the center, the eccentricity is larger, so this is more posterior, this is more anterior, okay? And along this axis, we move away from the calcarine, again, in early visual cortex. We have more foveas in the visual system, we'll cover them today, but in the calcarine sulcus, this means posterior, anterior, and this means away from the calcarine. Okay, and okay, maybe we have it here also. Let's see why I put this. Let's see if there's some added information here. So basically, what you see here again is the retina and the cortex, and I think it's just showing the same. Maybe it's clearer here because it's separated. So you have one R, or radius, or how far are you in eccentricity, and then you have the angle, right? And again, this represented in column or in rows in the cortex. So basically, this is the same. Okay. So good up until here, right? I think it's pretty. Most of you know some of it, or most of it, or at least a considerable part of it. But now I want to first talk about how we measure this, or how we measure this in fMRI, and then move from there to why we do that and how we can improve it. So, I'll see in a second if I have this stimulus slide, but what you want to do is you want to cover these two parameters in a very systematic way, right? So one way, if you want to cover the direction, you can move a wedge which activates a certain part of the visual region. If we're talking about early visual cortex, it's this flickering black and white checkerboard. You want to move it along this direction, or the other way around. And the other way you want to do it is have these rings in different distances from the center. Okay. You want to do it in an interval that will match what you're looking for and will cover basically the whole visual system. So what subjects are instructed to do is to look at the center, not move their eyes, and then you systematically do these two types of measurements. And we'll talk about it in a minute. It's very important that you do this in a very, very steady way. Because what you want to do later is you do a correlation analysis. Basically, we'll see it again in a few minutes, but you basically want to check which voxel respond to which direction or eccentricity best. Okay, so you test the activation of this voxel to all positions along this eccentricity axis and all positions along the radial axis, and you check the responsiveness of the certain voxel. So let's see if this works. Right. So this is a classic extracting rings, and you see you have a couple of seconds in each eccentricity. You fix it on the center, and what happens after you cover all eccentricities? It starts from scratch, and we call every such array of visual stimuli a cycle, and you carry several cycles within a certain session. So this was one cycle. You can do it, I don't know, 20 times, and collect data. And this is basically here. So you have time. Here it's very simplified. You have time 0, 20, 40, and 60, for example. Okay. And what you see in this schematic description is the expected response profile of area responding to the stimulus. So if the area in the brain that I'm looking at responds only to this, for the first, for example, for the first ring, for this kind of eccentricity, then I will get activity here at this time point, and I will get no activity the other time point, and so on and so forth. Okay, so this is a very simplified idea that and the main phrase to take from this is the phase. Okay, so what it means basically that if this brain of this region of the brain corresponds, different voxels correspond to different eccentricities in the visual field, so each voxel that corresponds to each eccentricity will be active in a different phase along the cycle. Okay, this is called phase encoding, and this is the basis for the first analysis we're talking about, which is the classical retinotopic analysis. So the corresponding radial stimulus is this one, and again you map very, very systematically the whole visual field along this round trip is doing now. And again, you have cycle, and you repeat the cycle, and if this, let's say, in a perfect way, this is exactly the width to which a voxel corresponds, okay? Then each voxel will correspond only to a certain time point, okay? This is it's never that perfect, but this is basically the thing. Now, finish. No. Question? No. So, okay, it doesn't finish, so I'll kill it. Before we get to that, first thing we want to, well, at least think about it at this stage, and we'll talk about it, is what do you mean a voxel responds, okay, to a certain point? Because voxels do not respond, neurons respond. We know we have a lot of neurons, 100,000 to 1 million, it depends on the size of neurons in each voxel. So why would they respond to a certain direction or a distance? It's not always the case, but the idea is what I talked about before, is that the neurons, and therefore the voxels, but first of all the neurons are organized in a certain way, okay? And if large subpopulation of the neurons in a certain voxel corresponds within itself, okay, they respond to the same stimulus, or the same feature of the stimulus, then the net activation of that voxel will rise or fall according to that responsiveness, okay? And because we have this retinotopic mapping onto the brain, because the same fibers represent a certain place in the visual field arrive at the same location as the visual cortex, then enlarge that population, that local population of neurons will respond the same way, more or less, and therefore the voxel will be responsive. Otherwise, we would get noise, basically. The neurons will cancel each other out, and of course, when that's the idea. Where in areas where we don't have any certain mapping, we cannot use this analysis. We can use this analysis, but it won't yield anything, and that's actually good. Okay, so how we approach this when we design an experiment? So this is a very, very simple idea that works very well with its limitations. So you know, like every experiment you do, you know the time points, right, of where you present each stimulus. In this case, you know the location and or the eccentricity of each time point, and you can build a predictor. And this predictor, in this case, is very simple. It's a periodic predictor, okay? Because you have a cycle in which you cover at a certain rate, you cover the whole, well, not visual field, but the whole set of possible angles or distances from fovea. Okay, so you can, for example, if these are the time points, and this is just a schematic of activation, so you know, so a certain direction, a certain eccentricity will be presented every given time, and then you can convolve it with the HRF, canonical HRF, and you'll see if the voxel, this voxel, responds to that particular position. Okay, ideally this will be the activity. Okay, of course it's never ideal. And then before I get to that, you can do that, right, forever. If you have here 1, 2, 3, 4, 5, 6, you have 6, let's say, different conditions, or you divide the circle to 6 parts. Okay, so each the ideal response for each of the 6 positions in space will be the different phase along your cycle. Okay, so basically you phase encode the space you cover. All right, and now you have basically a time course, the signal you have. And of course, it's you have noise and you have all these ups and downs in it. And what you want to do is you want to see for each voxel, because each time course is taken for a different voxel, for each voxels, and you can see which yields the most correlation. You can correlate this time course, the overall time course, with the 6 different predictors. Okay, each one corresponds to optimal response to a different part in the visual space. Okay, you can see if you correlate this to this one or to the one that moves one ahead, and so on and so forth, all the 6 possibilities in this example, you can see which one yields the most, the higher correlation. Okay, so here, here, this is a different predictor moving ahead 1 step in the phase dimension. And then you have another one and another one. Okay, you can see this all in this example 6 predictors, and you can do this correlation analysis. So it's very simple, but yields very nice results. This is okay. This is just I think Tzvi put it here. This is just to show you. This is the first time we see in this course some statistical maps. Proper statistical map, so this is just, we'll see something nicer in here, but this is just showing you that you can play with the thresholds. Usually this threshold is a statistical threshold which you set, but here you can set it to correlation threshold. You can see it, this is Brain Voyager, but the principle is the same. You have here, instead of T, which is the statistic, T values, you have your R, which represent your correlation, and you can see so before we see this, what did the algorithm do? What did the process do? It compared for each voxel this correlation, picked up the top correlation of all 6 predictors. Okay, the predictor that correlated with the signal the best, and it's a winner-take-all analysis. So if I have 0.1 to 0.7, let's say, for 6 predictors. I picked up the one that is 0.7 because it's the highest. Then I assume that this voxel corresponds or responds, the neurons in this voxel respond to the brain region that was the visual, the space in, the place in visual space that corresponds to that predictor. Okay, so now each voxel has one phase which was selected as the best describer, okay, the best predictor. But now I can elevate and choose only the ones that have a certain correlation, like a minimum correlation of, say, in this example, 0.4. So what will happen is that only those voxels that had some kind of high correlation with one of the 6 phases, one of the 6 predictors, will be painted here. Okay, the other voxels that do not correspond, correlate well with any of the 6 predictors, they will not appear here, and the assumption here is that they're not responsive in a specific way to that place in space, at least not to the stimulus I presented. Because we can play around with the stimuli, and we'll see that in a minute.
So we see here
Okay.
several correlations together?
Yes, you can see all correlation. What you can later is map them not according to the correlation value, but to the phase. And you'll see that in a second.
So you have a minimum correlation that you require.
Yeah, what you hear first, you put a cutoff, yeah.
If it's not correlated well with the signal, then of course it's not visually responsive. Okay, so you ask for a minimal level of correlation, and then for each voxel you assign the right phase. What the
So here we see the whole phases.
Yeah.
Yes,
Whole phases, you can see the area which are sensitive to location. Okay, but you don't know which location. Okay. Yeah. So what you do here is exactly what you said. This is just to show you that now the scale has changed. You see that lag is written there instead of before that it was just number. And this is again in Brain Voyager, but the idea here is that instead of 6 predictors, we had 24 predictors. Okay, we divided space to 24 parts, and now you can see each to which of these parts this particular or any kind of particular voxel responded, and again can play with the threshold. Okay, and now if we make it let's say reasonable threshold here, we can see that we suddenly get something that is much more logical. Let's see if I have here what I'm missing here is, yeah, I don't have it here. We'll see it in a minute. I'm missing the representation of space, like which is which.
Okay.
Yeah. But what you see here first, okay, so this is the cortex from above.
Is that the color? The phase?
Yeah, it's the phase, but I can map it the way I want. So I don't know if the blue ones are part of the upper right visual field or the lower left or what's that. So usually you show this together with a map, and we'll see it in 2 slides, that show you how you divided the visual space, and now you see which part responds to which part of it. This is missing from this picture, but you have to trust me when I say that this is actually reversed. This is the left side of the brain, so this is the right the right space. Okay, this is you see the RML, it's inverted. So this is the left visual cortex, and this means that the yellow regions are the right visual field. And these are represent the left visual field. You can see it from behind. So first, and instantly you can see this expected division between right and left. Okay, it's no big surprise, but it's nice to see. You can also see some gradient, and again, we don't have the scale here, but you can see that along this dorsal ventral, so this axis, you can see some gradient. These colors, the yellow and the orange, they're not randomly distributed. Okay, it's lighter as we go here, it gets darker or stronger as we go here. Okay, and this is again because the way we when we did this experiment, we color coded the space. Okay, and you can see it here. The back part, the posterior part is it's easier to see here. But you see this gradient, and this gradient represents, yeah, the next slide. It represents also a gradient that exists in space. Okay, so for example, this voxel, again, I think the idea here is to show that it corresponds best to maybe this color. You have to remember that we have the HRF, which is a bit delayed. So let's say the orange part, the peak of the orange, if something responds to the orange part, the peak will be a bit after. So we know we have the HRF canonical function, so we can derive the responsiveness out of the signal.
So just to make it clear, so you have a delay, right? You have a delay of maybe 4 seconds, so you have to move this backwards.
Yeah, but since we created this predictor from the impulse function and the HRF, we know exactly the delay that we need to take into account. And as I said, if we take a random voxel which is not correlated to each one or didn't achieve a high enough correlation to neither of the predictors that we have, then we get some noise. And this is just an example. You can basically see it, but it was also analyzed that there is no particular predictor out of the 6 that explains this the data that we see here very well. Okay, so right here at last this is what I talked about before. Okay, so just to explain what I mean, we have here the visual space. Okay, and we have here the left visual space, and we have the bottom part and the upper part, and you can see that things are color-coded in a very systematic way. And you would expect to see some kind of gradients that correspond to these gradients in the cortex because of what we said, because how fibers get from the LGN into the early visual cortex, and that we have a very, very systematic way of organizing things. So what you see up there, let's start from this small image because it's the easiest one to navigate through. So the obvious thing that you should see is that the bottom part is represented in the top part of the visual cortex and the top part of the visual field in the bottom one. Okay, that's very clear. We don't have the other, but if we have the other visual field, we'll see that. What we see here is a flattened map. I mentioned it once in the first or second class, just that you won't see it. That the purpose then was that you won't see it for the first time now. But let me guide you through it. Let me see if I can guide myself through it. Okay, so you have the slides here. Let's see, this is the one. Okay. Right. So you have the calcarine. Right. You have the calcarine. Okay. Oh, okay. So, yeah, maybe you should.
I'll have it.
Yeah.
Okay, so that's what the flat map. First, look at this one. I didn't mention this one. Maybe it will. I'll be teaching this in the next session as well. So maybe that's. What so you see here the sagittal slice, as Yuval said. That's the coronal slice, just to orient you. So sagittal is like this, of course, right? And coronal is like this, right? Okay. So and you see, as Yuval said, orange corresponds to upper visual field. So this would be the calcarine here. That's the sulcus where V1 is. Okay. Bottom part of it maps the upper visual field here. Upper part maps lower visual field, as Yuval said. Now you could look at this as the flattened map. So what you see here is cortex. Maybe we'll look here. This is the same hemisphere as we've seen here, but now you can see the foldings that I think you've already been through. So the darker areas would correspond to the sulci. Okay? And what you see again, it's very similar to here, but you can see this across the sulci as well. So it's basically a similar picture to here. And what you see here is just a flattened map. So
this is the calcarine, right? So
yeah, so you got the calcarine here.
Yeah.
Okay? So again, so the lower part corresponds to this, so this would be lower calcarine, and this would be upper calcarine. And the important thing to notice is what are these dots and lines here. So the dots here correspond, look what the color is. The color here would be of the vertical meridian, you see here? Okay, so it's like dark red here. And here, it's the vertical meridian, the lower vertical meridian, this one, and red corresponds to upper vertical meridian. Okay? And you see that we know from physiology that the border between V1 and V2 in terms of neurons, if you pass an electron, record the receptive fields here, okay, would be of the calcarine. So let's say you're making a penetration going from here further and further. So you'd be moving in a specific eccentricity from the horizontal meridian, yellow here. As you're moving to the border between V1 and V2, you're going to get to the upper vertical meridian because you're talking about the lower part of the calcarine. So this is the border between V1 and V2. How do we know from the physiology? Because the cell's responses change as you move from V1 to V2. First, the receptor fields become much bigger, maybe 2 or 3 times bigger, okay? But they map the same area. So we don't know if the border exactly between V1 is here or here. But we know that this is sort of replicating what we find from the physiology. So as you see here, there's a division. V1 to V2 is exactly this hatched line. As you're moving forward, okay, you see the border between V2 and V3, or what's called VP when you're talking about the bottom part. So that would be here on the vertical meridian, on the horizontal meridian. So the yellow here, okay? As you're moving here, you're going to the vertical meridian, now you're going, and you're ending up in the horizontal meridian again.
When you're inverting the direction you cover this cordon, then you're moving from one area to another.
Yeah,
right?
So you're all the time, if you're sort of in the lower part, you're all the time mapping the one quadrant. In this case, the upper left quadrant, because this is the right visual hemisphere, okay? And then, so there's a clear prediction of how the receptive fields would look like as you're moving with the electrode. And so with that, basically we replicate what we find in a monkey, the nice retinopathy, and the idea is that nearby cells have overlapping receptive fields, okay? So it has to be this way. There's no other way. If you're moving from V1 to V2, you should be having, as you're moving, let's say this is V1, now you're moving to V2, they map the same visual field, same area, receptive fields have become bigger, but they map the same area. So it's a continuum here. There's no breaking point here.
And between V2 of upper quadrant, lower, there is no continuum? They're separated?
In the same
No,
V2,
so
they are located in a different on a different side of the calcarine.
So there you have this valley here, and as you said, it's from different sides. The upper calcarine maps the lower visual field, and the lower calcarine maps the upper visual field. So indeed, they are separated. Okay, there's the valley, and there's 2 sides of the valley.
Right. So if this is cut here, so usually when you don't cut it, so the green, let's say the green V1 will be here, and then the green V2 will be here.
In B you can see this. I mean, this is how it is
In
actually
B,
the brain.
exactly.
Okay, here we just flattened it, so we had to cut some place to flatten it. So these are actually adjacent to one another, just different sides.
Right.
Okay.
לא, בסדר, נעשה עוד 5 דקות, אני רוצה רק, we'll have 5 more minutes and then we'll have a 5-minute break. Okay, I just want to make maybe two remarks. Again, like I said, what we're looking for is the optimal phase. So we're looking for the best fit for our data. And this, keep that in mind. I think I'll try to get that in the last few minutes of our lesson today, that we don't really analyze the whole. We have a lot of data that we're not analyzing. For example, we have the receptor field size, which we're not talking about. We're talking only about responsiveness to a certain eccentricity or direction. Of course, if the size of the receptor field is very big or very small, it would affect our ability to map. Okay? Why is that? You have some intuition to that? If I have a very large receptor field,
then too many cells are like many regions. It's not specific to
Well, it will respond basically to several several orientation or several distances. Okay, you have a the resolution of the map would be very suboptimal, but there are ways to use the data better, or even better to plan a different experiment that uses data, and that is the population receptor field, which I hope that I will again touch very briefly today. Maybe Udi can say a few words next week. Peter here knows these guys very well. This is one thing. And another thing is, before we go to the break, this is less important, but we can use basically the same kind of method, which is finding the best correlation, doing phase encoding analysis, correlation analysis, to map not only early visual cortex, but other visual responsive areas. But these require to have a certain stimulus. Okay, so you have to design your stimulus in a way that it will activate in a very certain way. Okay, you have a certain prediction of how this region, of course, is organized or responds to which kind of stimulus, how the map you think it will be organized, and then you can create stimuli to try to map this organization in an optimal way. And I'll go over it, I think, maybe after the break. So we have a few examples, and then we'll go into the population receptor fields. טוב, קצת את הטובי? charge of all the academic stuff. I really don't know. No, the Moodle is one thing, but that's not what's important. If you want to credit that, the Moodle isn't the thing. The thing is be registered in the UG system. So maybe
you
I'll
want to start at 3 or
yeah.
you want to start now?
Wait a minute. It's
4.
4.
4,
Let's see.
sorry.
Now it's 4. Yeah.
Ah,
I don't know if this thing works. Maybe it is. Maybe it's just that minute of the day that it shows the right time. We'll see in a couple of minutes. Okay. I have now several examples of how we approach, how we use this this approach to map different. No, this one doesn't work. How we use this approach to map different parts of the visual system. I'm not going to go over all of them because it's kind of repetitive. But again, from the 90s, this was repeated at several different experiments, trying to map several different parts of the visual brain, parietal, occipital regions, using different stimuli and or different frequency of signal. Basically, how you map. Let's say you can again. Let's say it was done in steps of 6 steps, or 24 steps, and so on and so forth. Depending on how again you think you can model the data according to what you think the resolution in that particular region would be, and you can have a kind of idea of that from monkey research and so on. You can think about this activity as some kind of a traveling wave. Again, you have here some 3D illustration of that. You have the signal amplitude, which is you see the rises and valleys here. You have space and time. Time goes from left to right, and you can see that these lines are not straight, they go like this because this is space. So you move this traveling wave along space, right? Covers a certain a long time, goes through the space like this as we move forward in time, and then flips and starts again. Okay, depends. This is just an example. Depends on the exact stimulus you have, and what you can do. And this is basically covering what we did before. You can take this a step further, or just to analyze the data a bit further. It really changes not a lot, but you can estimate how good your model cover the data, or basically match data, and from that say something about how this region that you are testing now is organized, if it's organized to principle, if you are able to map it in a systematic way using your certain stimulus set, then you have discovered some kind of mapping principle. And you can analyze your data, put it in the frequency domain, okay, and see that traveling wave we saw, or basically your time course, your data. You can see the division or the histogram of frequencies, basically cycles per scan, and see if you have a dominant peak at the frequency in which you presented this stimuli. Okay, so for example, if you have let's say, in this one, how many cycles per scan? Don't remember. But let's say if you have I think it's 6. Let's say it's 6 for the because this is 12. You have 6 cycles per scan. So if your stimulus was 6 cycles per scan, and you have a certain peak here, you can now estimate your SNR, or the reliability of the mapping, as the ratio between the peak at the relevant frequency of cycles per scan relative to your other well, the level, the baseline level, or the power across all frequency. Okay, so you have the power of the desired frequency and the power of all frequency. Here you can see that you have a very nice peak at 6 cycles per scan. You also have the harmonics at 12. Okay, you don't see it at 16. This is basically 12, and of course, if you do 6, you have 6 hertz, or not, it's not hertz, but 6 cycles per scan. You're also going to have some kind of frequency at 12, all right, 12 or 18, and the different harmonics.
How do you calculate the percent modulation?
The
percent modulation? What is 0, 1, 2?
percent was here. It's just arbitrary. What you usually do is you think in this case you don't have a baseline, so you just it's a good question. I have to think. What?
The bulk signal.
Yeah. But how do you extract exactly the percent signal change? I'm not sure. I'm not sure if you do it directly or you do some manipulation. I can check it in a few minutes. After it will take me a few minutes to see how they did it in this particular article. But basically, we divide. It's a bulk signal, but I'm not sure if they did some kind of interpolation. So here you have again this 6 cycle per scan, and you take a certain amount of, so not a certain amount, a certain area in the brain. Okay, you can take a certain area, you can take the whole visual cortex or the whole brain and basically cut off a certain coherency level or a certain, you can do it in both ways, or either cut off the percent modulation or this ratio between this peak and the overall power. You can take that, or you can take what we did before and threshold the R value, the correlation value, and you get certain voxels that are show reliable mapping, basically. Okay, so you can either show that they have the correlation, which is, let's say, about 0.4 or 0.6. This means again that they corresponded to one of the predictions that we have in a satisfactory way, okay, in a high correlation. And again, you can check the reliability by doing this, okay, by checking the cycles that you have for the task against the power of all other values, okay, at the baseline. You move the data to frequency domain by Fourier transform Fourier, and you get basically a spectrogram of the cycles that you have, and you can analyze the overall power and the power of the desired cycle per scan. And what you see here, basically, wait, I'm going to skip a few of this because these are just a bit redundant. Okay, let me go back and we'll start from here. And what you see here, again, is these two data sets. Okay, we have this eccentricity and the radial mapping. And as you go to the extrastriate regions, they are mapped HV4, VO1. We see a couple more. Well, what do you expect, or how do you expect this representation to change? Will it be there from what you know, or what you're familiar with, or what you know from monkey literature? Will they be more precise, less precise? Will something systematically change?
What's the change according to what?
You're moving from the early visual cortex to the more higher level visual area. So
Bigger receptive field?
bigger receptive field, okay, and we said already that will, would you expect that to do to the mapping?
Lower resolution?
Lower resolution, lower specificity, basically, okay? So you expect this gradient to be less and less clear as you go, but, and this is important, you do find this representation. And you find this representation all along the visual stream, both ventrally and dorsally. Here you look at the ventral region, so maybe I have some map that covers all of these regions. Okay, maybe we can see it here, at least a bit of them. Okay, so here again you have the inflated brain. This is the lateral part, so this is the early visual cortex fovea, this is the occipital tip pole. Okay, here you see the same region, this is the medial part, so here we look from the inside of the brain out. Okay, this is the corpus callosum. So these two brains are basically the same brain region from two different viewing angles. What you see here is the dorsal pathway, ventral pathway, and semi-dorsal. This is also part of the dorsal pathway. Okay, and these are all regions that show some retinotopic mapping. And by that I mean that they show some sensitivity to angular position, some sensitivity to distance from center, to eccentricity, and they have a certain, let's say, we didn't touch that, but they have a certain size or I would say representative size of visual receptive field, which we'll touch in a bit. Okay, so you have here, and this is just to go over more or less, you have the early visual cortex V1 to V3, then you have on the ventral part human V4, then VO1, VO2 now, okay, and then you have human MT here, part of the dorsal stream, you have LO, you have and IPS, which is the interparietal sulcus, going into the parietal cortex. Now, just to make one thing clear, we're talking about all these regions, and sometimes every few years there's another region that pops out. Okay, I just one quick word about the logic behind these regions, so naming and defining them. So usually people refer to monkey literature to see, you have some kind of regions that are well defined from that literature. For example, the MT, okay, which is the middle temporal. Again, this is this is human, but in monkeys you have the temporal lobe and you have the middle temporal lobe, and there you have some voxels that are sensitive to motion. Okay, so here so people look for the correspondent region in humans, which is the human MT. So some of these regions have corresponding regions in monkeys, some don't. Because some were defined only by the existence of a certain phenotopic map within them. Okay, so for example, region VO1 or VO2, okay, which are here in the ventral stream, were defined as regions which have their own quote-unquote phobia. Okay, so they have a independent, let's say, map from the neighboring region. Okay, which has some kind of mapping. It's not as accurate, okay, as specific as the early visual cortex, because again the receptive fields are much larger. But they have some regions. It's mapped in very specific way, in which the phobia is represented in one point. Then you have a gradient of eccentricity. You have gradient of location. Okay, again, as you move forward, receptive fields of the neurons start crossing meridians sometimes, or just encompassing the whole visual quadrant or visual hemifield. So you disperse a bit, but still these kind of regions were defined exclusively by finding these retinotopic maps. Okay, so there's a big, I would say, in the last 15 years or something else, even 20 years already, that a lot of group with the magnets are becoming stronger, the paradigm is going to be more sophisticated, and people are able to come up with new designs and test some new models and find more refined maps. Okay.
Did you mention something about what is becoming more sophisticated? Did you mention this?
Well, I don't know what you mean, so maybe, yeah.
Okay. Well, the point is that typically when people map the V1 or V2, early visual areas, they use this.
Yeah, we talked about. We covered this. Okay,
Yeah.
the classical one.
So these are the classical ones where you have this checkerboard, right? This flickering checkerboard. When you go to higher order areas, typically they don't respond as well to these checkerboards. And there you should use either faces or buildings or something like that. But they could do the same sort of. You could use a wedge of, let's say, faces and turn that, or a wedge of buildings, or a wedge. Okay, and
you manipulate the spatial location, but with the matching, with the corresponding
so this
stimulus.
was using a more optimal stimulus for these higher order areas. So that was part of the story of how they got to map these higher order areas.
And for example, regions in the parietal, the IPS, were mapped using a delayed saccade test. Okay, so you have some, you fixate, and then you have some kind of target, which you are supposed to make a saccade. There is some kind of delay, and you have to represent the saccade target, right? So you look at the fixation, let's say. Now you have a target here. You know that you're going to make a saccade here. You wait, then you make the saccade, and you come back. Then the target is here, and so on and so forth. And you can use that kind of paradigm to map regions which are associated with the preparation of saccade. So, of course, regions that have no spatial relevance, or they don't deal with anything that involves spatial encoding, there's no logic behind trying to map this to see if there is a mapping of space. But these regions which participate in in some test that has a very strong spatial element, okay, directing of saccades to a certain location. You need some kind of a very good representation of space for that. So use the correct task. So it's not only, I would say, what Udi said, it's not only the stimuli themselves, but also the task. Okay? So this is how you would define these regions. And again, you can't see it very clearly. Like we said, the receptor fields are larger and stuff, but you can still see these inverse gradients. Okay? You cover the visual field in one direction, and then the direction changes. You cover it from here to here, and then back. And whenever you inverse it, there is a boundary between regions. Okay? So with the correct stimulus, correct task, you can map very distinct and very widespread regions. And this is just to continue to cover, again, it's not important for me, the exact combination of regions, because again, it depends on your task. Sometimes it's important to know in which, let's say, if you're on VO1 or VO2, because they have two different phobias, but sometimes to your task or to your research question, it doesn't really matter. What matters is that you're in a region that represents objects or faces. Okay, but in general, you have dorsal, let's say, dorsal regions and ventral regions. You can add here up LOL2. So this is again a very, very, very schematic. This corresponds to that one. Very schematic description, spatial description of the region. So here you have the calcarine and occipital pole. You have the early visual cortex. Okay, and this is a very, very, like I said, consider the brain flattened and in a very, very simple, minimalistic way to present it. You have this is basically dorsal, and this is the lateral part of the dorsal stream. So here you move straight to the parietal cortex, and along the lateral banks of the temporal parietal cortex, and on the bottom part, the ventral part, you move to VO1, and then you get into regions that again have some spatial specificity, but as you go further and further, you lose that specificity, and finally you get into the most anterior region, let's say in the ventral part, where you have a very distinct, I would say, functional specification, like the FFA, or the TPA, which represents supposedly, there's debate on that, but supposedly represents scenes, and the FFA, which represents faces, and onto the parietal and parahippocampal gyrus. And also there, if you potentially, well, in the end, no, in the end of the pipeline, you get very, very large receptive fields, so you lose this kind of specificity. But along the way, if you use the right sets of stimuli, you can get some kind of mapping. Okay, so I have maybe 20 minutes to present at least the idea of a population receptive field. But first of all, I want to make sure that we get the retinotopic mapping thing. So it's really not complicated. It's the idea that you can, first of all, that neurons in the visual cortex are organized in a very certain way that is affected by the wiring that comes from the retina. Okay, we have the retinal map, which is we can describe in 2 dimensions the radial direction and the eccentricity. You map it into columns and rows, basically. In the early visual cortex, these columns and rows align according to the calcarine sulcus. Okay, so along the calcarine, you move in eccentricity, and away from the calcarine, you map this. You map basically the angular direction from the fovea. And again, you map it. Just 1 second. You map it as you cover one coordinate. You cover like this. With something it's better. So you have this coordinate, and you map something like this, and then you map it the other way around. And as you go in this, you move away from the calcarine. The calcarine is something like this. This is you move like this, and that. Okay, and you have V1 here, V2, V3. Okay. So we have these two parameters that you use to describe the visual field. You map them into the 2 axes. Later, when you move from the striate cortex, you move to, let's say, LO, you move to MT, you move to regions. You can describe the mapping with these 2 parameters still, with the radial direction and with the eccentricity. However, and it's organized, so you see this nice foveal maps, right? But you can the rule of the calcarine is of course not there. So you can still see the gradients, and you can still see, if you see, for example, here you can see the eccentricity. So this is VO. So you see some kind of fovea here, okay, for example, and you can see that there is some kind of consistent mapping going from middle to peripheral, okay? So the same concept is
a little quiz, just to see if you figured it out. Okay, so Yuval just showed you this here. So just to orient you, that's the back of the brain. That would be posterior here, moving forward here. Okay, and let's say, so this is, let's say, the left hemisphere that you're showing. Well, what if we move from here to here to here to here to here, along the calcarine sulcus? So going more anterior. What happens to the receptive fields of the neurons?
More peripheral.
More peripheral. So we're on the horizontal meridian, so that's the visual field. That would be the fixation. We're fixating. So receptive fields would move from here to here to here to here. They're becoming bigger as we're moving in eccentricity. So that's along here, okay? Now what if we move, I think Yuval mentioned, okay, we're here and we're moving up. What happens to the receptive fields?
It's the same.
So we're at some eccentricity, so let's say we're here, and we're moving up.
It's down.
Right, so they're moving, not down, but they're moving at a given eccentricity, same eccentricity, and they'd be here, 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 and here. Okay, so that would be 1, 2, 3, 4. Now we get to the border of V1 and V2, where are we? Right here.
Going back.
Okay? And here, we suddenly see now, as we're moving to V2, suddenly the receptive field becomes something like that, much bigger. That's how we know we move to V2. And then as we move here, we're going back to here. That would be again, so that's what Yuval drew you to you, this borders between V1, V2, and V3, and so on and so forth. And this is just a complex way of portraying this. And to make things more difficult, you have a flattened map. Each group has its own way of flattening the cortex. So it's very, so you see here, V1 is like in the center. And the one before that,
V1 is on the side.
The V1 is on the side. So that's just to make things more complicated. But don't be confused by that.
So how do you separate between regions?
So
You
we
find
know,
the-
okay, we
you
just
find the
explained
meridian.
how we have to separate between regions.
But by the map?
Vertical meridian
No,
or horizontal
can you go
meridian.
back to the previous slide?
Let's see here, for
No,
example. No?
No.
Okay, not
Here you
problem.
can really
Here-
see-
Here's a
see-
flat map here,
see-
okay?
yeah,
So
forget
here's
the-
V1. You go this way.
Ah,
You go
because you already
ventral, and
started.
here's the border between V1 and V2. What is it? It's the bright green color. What is it? It's right here, okay?
You move from here, you
Yeah.
reach the peaks, and now you're going back.
Yeah, and you go from V2 to the border between V2 and V3, and you're back on the horizontal
Okay,
ring.
so once you covered a region, then you start different.
So you see that, okay, yeah, from here, this is this is V1. Upper side, lower side of V1. And then the border between V1 to V2. Now, in V2, you have a sort of a map of the quadrant, which is a mirror image of what you just seen.
It's important to say that, of course, it's not guessing. We know that from animal research. So you can do the histology of the animal, and you see that where the meridian change, you have, like Uri said, different cells, right, with different receptor fields. So we know that this is the
So the point was that this is a relevant point for, okay, why is fMRI a useful tool? Because it replicates what we know from the physiology, okay? So without it, we'd be completely lost. Why are we using this technique? So that's in terms of phase angle, in terms when you're using the rotating wedge, and that's the eccentricity now, right? So you see fovea, there's a sort of magnification of the area which maps the fovea. And as you're moving, that's in if you notice, this is in an axis which is orthogonal to here, okay? So, as I showed you before, if you move from posterior to anterior, yeah, then you're moving along eccentricity. So this is the most posterior area of cortex, and as you're moving here, it's more anterior.
Yeah,
So
but
the flat map is
these
hard to
maps
see.
are horrible. You saw that I was confused in the first.
Yeah.
I find them horrible. It's nice though to understand the concept. Okay, don't try to figure out the physical what.
They're easy to understand the concept, but they're difficult
To map the exact location of the brain.
Where are they
Yeah,
in the
yeah,
brain?
yeah.
That's not,
But the concept is clear, and this nicely brings me to at least the idea of that I want to present of population receptor field, because I mentioned this briefly before, but we're not doing a very optimal analysis of the when you're using a we do classical retinotopic mapping. And what do I mean by that? First of all, you use a winner-take-all method. What does that mean? That I found the maximal correspondence, or the best correlation, and I decided that voxel correspond to that certain location. However, if we go back to neurons, we know, you know how a tuning curve looks for neurons, or let's say, is it something like this? No. Is it something like this? If this is position in space, let's say 10 degrees, 1 degree, 0 degrees, minus 10 degrees.
No.
Right. It has some. Yeah, of course it's not. That's the reason I'm asking it. But where's the black one? There's a purple. Blue one. But you have some kind of a bell-shaped curve, more or less. It's not exactly like that. But let's
spatially. I mean, in terms of
spatially,
space.
yeah. So here is the degrees again. This is I don't know, 0 degrees, or let's make it. This is 10 degrees. This is plus 20. This is minus 20. This is 0. Okay. So you have maximal response, but this neuron is responsive to adjacent location. Okay. And again, the receptive field is changing, and the receptive field size determines this kind of curve, this responsive curves. So when I divide, I have some resolution that I divide space, and I decide that this voxel, now I'm talking about voxel, corresponds to this position, but now it depends on my spatial resolution, how I divide the space. But let's say I divide it fine enough, so I have also this position. That's the next phase. And of course, it will be less correlated to this one. So I will eventually, after running all the algorithms, decide that the certain voxel responds best, correlates best, the time course correlates best to the phase that corresponds to 0 to 10 degrees, and I will say that that voxel responds 10 degrees, but of course that's not exact. If the voxel has the same kind of tuning curve as the neurons within it, which is nothing assures that it does, but
No,
we
we
are
know that it does. Okay, okay.
yeah.
You're going to talk about this? or-
Yeah, but it's a good.
We know that it doesn't. Okay, the point is that when you talk about neurons, that they have a given receptor field. Okay,
Yeah.
so let's say that they have,
Yeah,
and
I'm
neuron has
gonna
one
talk about it,
receptor
yeah.
field here.
No.
We're about to talk
No,
about.
no, I'm gonna.
Okay, another, the nearby neuron, if you were to recode from it,
Yeah.
has a very similar receptor field.
That's
Very,
here
a
it is.
great overlap between the two, but it's not
Here
ideal.
you have it here.
Okay, so here's one, here's the second one, here's the third one.
These are neurons, and the red ones
Okay.
are.
Now think about a box
here.
that has a million neurons. Okay, so once you have a million neurons, this jitter would lead to the fact that your population receptor field, which is the average of all these million neurons, is going to be bigger than each individual neuron. That's for sure. Okay, how much is it going to be bigger? What is the ratio between them? Is it going to be 3 times bigger or 100 times bigger? That's a question of what is the jitter in terms of the receptor fields, but they are going to be bigger. So, but
in any case, yeah.
yeah.
No, in any case, this is, you miss something, right? When you reduce the response to a winner take all response, you miss something of the, you don't describe the response very well, okay? You just decide, you assign a maximal response to each voxel. So this is very helpful for us in determine things like recognizing the meridians and understanding which region holds a retinotopic map and where this one region ends and the other begins. However, if we want to describe better the response, we can do something smarter. And well, and especially we can take in we can try to model again what we say. We try to model the average response or the overall response of a voxel, of the neurons inside a voxel, in terms of the not only the location, which were the responsive, but also the size of the receptor field. Okay, we can try to get something like this bell-shaped curve. Okay, describe the response of a voxel in a bell-shaped curve, or at least estimate it, and get more specific estimation. So this is just to remind ourselves, forget the headline now, that as we move further along the visual hierarchy, we get to larger and larger receptive fields, okay? Usually these neurons here incorporate information from numerous upstream neurons, becoming more specific to the content they represent, but less specific to the space. So this is the logic. Okay, so the basic logic is to try to describe the responsiveness, the spatial responsiveness better for each voxel in a way that will somehow be similar to what we describe when we describe the single receptive field. And this was first done, I think, by Serge Desmoulins and Brian Mondale's lab, and been done many times afterwards, also in our lab, in Udi's lab, several different ways. And the way they did it in the beginning was taking the classical retinotopic mapping that I talked about and adding a very important element into the task. So let's see, this is a classical retinotopic mapping with this rotating wedge. You see the timeline, you see the wedge moves and cycles. Here we have depicting four steps within a cycle, it doesn't matter. And this is typically, this is what you'll get. I don't know if it's a real example or something that, I think it is. Yeah, looks like a real example. From two regions, very different regions, and we know they're different, first of all, in their functionality. V1, of course, the primary visual cortex. LO participates in the presentation of objects. Okay, we know that they're located in very different ways along the visual stream. And we know, except for the functionality of that, also their receptive field size is very different. Okay? We that from animal research. I'm talking about neuron receptive field. Okay, and this is how the signal looks like. Okay, and you can see in these arrows the time points in which the optimal stimuli was presented. Okay, so if you take here, you have a cycle here, right? You move the wedge, and here it gets to the optimal optimal wedge that excites this
optimal
wedge
polar
position.
angle of the wedge,
Yes,
right?
optimal wedge position. So
we
it's a
take
bit
a look at
before
the-
the peak. So you can see it here now. Let's say it's this rotation, this position. Okay, along this rotating wedge. Now it's here, and every time the wedge arrives at this position, these are the time points, and then a bit after that, you see this peak activation. Okay, and this is the same, well, not the same response, but the response to the same stimulus. So they're both these two voxels taken from two different regions respond optimally to the same wedge.
Wait, a few
Yeah.
comments here. Remember what we talked about? You remember what we talked about here? They were using this checkerboard.
Mhm.
You see the modulation
Yeah.
in LO is very poor compared to V1. Okay, so that's a problem here. It's not ideal in that
Mhm.
sense, but you still see that there is a modulation. Okay, with the rotation of the wedge. But now, before Yuval supplies you with the answer,
Okay, yeah.
let's think about. Okay, now let's say that you have a large receptive field. Okay, let's compare the. That's just to be deductive, for letting you think about it. So, okay, here's your fixation. Let's say that in LO you have, in V1, this is the receptor field of the neurons, okay? And in LO, it's something like that. It's much bigger, right? What is the expectation? How would that be reflected in what you measure in V1 versus LO? It's a question to you. You know the answer. Okay, think about it. Okay, so you have this, remember you have this rotating wedge going tack, 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 yeah, like this. Okay, and again, it gets into the receptor field, comes out of the receptor field. When does it get into the receptor field of the LO? Much earlier, right? But it's like that. So it'll be responding, out of the receptor field, okay? And no response again. Okay? For V1, it's much smaller. Now, okay, you're not talking about one receptor field, but population receptor field. So if in V1, one cell is like that and the other is like that, and like that, well, the population receptor field is going to be bigger, as we said. But it's the same thing for LO, okay? So for the LO, I have to draw this in a different color, but you're going to get the same picture. So, in general, you expect that the population receptor field in LO is going to be much bigger than in V1, and therefore the response should be what? So if this is in V1, how should it look like in LO? If I were to draw the response to the same stimulus in LO,
It should be wider.
it should be wider, exactly. It comes in, it comes out, it should be wider.
But it's not what we see.
Not exactly. Okay.
Okay, so look, so why don't you show the stimulus? I don't know what next they show, but I guess that
Okay.
it should be wider, and indeed,
It should be wider, but yeah, what they did is added two epochs of basically blank screens. Okay, that the whole screen was gray, which is the average of these the black and white. Okay, so the total luminance was the same, but in a way that did not activate. Basically, shouldn't activate the voxel if it's responsive.
you get a baseline.
Okay.
Right?
Yeah, you get a baseline. But now think about what Uli said. So if you are if you have this rotating wedge, okay, I forgot to say something very important. So they did that instead of doing the corresponding phase steps that had to be here. So for example, you move here clockwise, right? You move like this, and then you get here, and you skip this one and this one, and you move straight this one. Okay, so you skip two, and you do this in the same ratio. Okay, so any idea what will happen in the timelines of these of two different neurons, or two
If
different
you are
receptors?
in the receptive field, or
Sorry?
it's in the receptive
what you have. You have a blank screen. Right here we have a blank screen. Let's say if I have a very large receptive field, okay, that covers this, but also covers what was supposed to be here. This.
It will sharpen the response.
Yes, but in what way? Okay, if I had something that's supposed to be here, and now, let's say the voxel in LO was supposed to be active this whole time. Okay, voxel in V1, for example, should be active here. If it's active here,
No.
no. Okay, because it's nowhere. Let's see what it does to the signal. So what you see here now is the blank epochs. Here, every cycle, they added the blank epochs at different points. And you first describe what you see, and then maybe we'll talk about it. So what's the difference between, let's start with the LO. It's much more clear, I think. What do you see there?
It's wider, right? Much wider than...
It's wider and...
F is much wider than E, right?
And there is some kind of inhibition maybe in the gray area.
What do you mean inhibition?
That it goes very sharp.
Compare first of all not E and F, but D and F, okay? You're right, what you can actually see here is you can see the size of the actual size of the receptor field, because you see when it stopped, well, you go back to baseline, right? You're with me? You go back to baseline here, because this, this voxel was responsive, should be responsive to this all epoch here. And what you see here, basically, is that even though, wait, I think I'm confused.
I don't remember this slide. So
Yeah, no,
I
I'm
can't
trying
help you
to...
here. But the basic question, the basic
No.
thing is that you get a wider response.
Yeah, of course.
Okay? Now, here, this is the blank here. You're saying, okay, why do you get a response here? If it's blank, why do you get a response? Are you sure about this being a blank, or what is it?
Yeah, it is a blank.
Isn't it just the ball delay?
Yeah, this is the ball delay. This is the ball delay. There's no... this is just the ball delay. What you see here is the response for this one, right? I think it's...
But it doesn't make sense in the LO.
Yeah, I'm trying, now I'm confused. I'm trying to see. Let's think about it together.
I think the arrows here correspond to the optimal,
optimal
position. Is this now done in a sort of continuous way?
Yep. Yeah, it's strange. I had it
I
proper
guess
in my
here
mind.
you don't get a response because now here you're covering the direction, the relevant directions, right? What is the optimal direction? It should be something which corresponds to this here, right?
Yeah, the bottom one.
Yeah, and now here